It's a great pleasure to introduce today's seminar speaker, Simone Melchiona. Simone got his undergraduate education at the University of Rome and his graduate degree there also. Following that, he spent some time in Lausanne at the École Polytechnique Fédérale de Lausanne, working with various groups there on electronic structure calculations. And after that, he went to Cambridge University, where he did simulations on condensed matter systems. After Cambridge, he returned to Rome, where he has a position at the, let me see if I can pronounce this correctly, Consiglio Nazionale della Ricerca.
Exactly.
Okay.
Very good.
The National Research Council of Italy. He got involved in a project that Sao Rosucci and some other members of my group, Maria Fita, in collaboration also with Joy Sirkar, were working on, involving multiscale simulations with the ultimate goal of doing simulations that are related to blood flows, hemodynamics. Simone worked on that project for about a year with the support of IAC. That was last year. And then this year, we are very fortunate to have him join us for an extended period as a member of the Cyber Infrastructure Lab. That's the CI lab there of the School of Engineering and Applied Sciences. And it's wonderful to have him here. I thought it was a great opportunity for him to present the things that he's been doing and some of the ideas that he plans to work on. So the floor is yours, Simone.
Thank you very much. Okay. I'll make the environment a little bit more comfortable. Thank you very much for being here and for the kind invitation of presenting these recent exciting results. And thanks to Tim for the presentation. It avoids me from explaining the first slide, basically. The first slide tells you about new challenges in multiscale computing. And before showing you some results about biopolymer translocation and hemodynamics, I need to define what a multiscale approach is. I want to begin from this painting here that I like, because it tells us a bit about a multiscale environment. This is a boat sailing over troubled ocean, and there are a number of things happening in this system. Well, at first, microscopic objects are moving at the molecular level here, at the water level. Atoms and molecules move according to thermal agitation in a rather chaotic way, and they create microcurrents, which is mass transport, momentum flux, and so forth. So small currents at the spatial and temporal scale. If you go to a larger scale, though, you would see more coherent waves, like tidal waves, the wind happening at a large scale, friction happening at the surface, at the interface between the boat and water. And finally, if you take all these things together, you would have an overall motion of the boat. But it is important to think that the system is really a linked hierarchy of events going from the micro to the macro scale and vice versa. So it's really a hierarchy of cause effects. So if we want to treat this system, we need to approach it in a kind of a diverse type of thinking, which is a multiscale type of thinking, because we need to basically fill the gap going from the micro to the macro scale. So let us idealize this boat and think of it as a sphere moving in a fluid solvent as what is called the kick particle textbook example. So imagine you kick the particle at time 0, and you follow the memory of the velocity of the particle over time. So this is typically a time correlation function. If you follow this memory function here, you would see basically 3 different regimes. A first regime at short times, which is basically due to the collisions of the molecule, of the moving particles, with the molecules of the surrounding solvent. These collisions are basically driven by the inertia of the particle, so it would decay in time with a parabolic type of behavior. After some time, this regime would change, a time which is basically given by the inverse of a friction. It's called the Stokes friction, and a new regime sets in, where basically the solvent would rearrange around this particle, creating basically these streamlines, which are kind of laminar in their shape. And they're basically due to the fact that a longitudinal sound wave is propagating out of this moving particle. The decay of the velocity of this particle now is basically a pure exponential, and the only parameter governing this exponential is, again, Stokes friction gamma. Now, the story is not finished, because if you wait for long enough, a new regime sets in, which is basically the propagation of a transverse wave, basically shear modes, which propagate away from the particle and create vortices. And basically, this would create a different regime in the decay of this function, which is no more exponential, but is now algebraic. Basically, this means that these sound waves are propagating at a distance which is given by the diameter of this particle. Now, this is a typical multiscale environment, because there are 3 regimes happening at 3 different times. This is also quite nice because it reminds us of Aristotle's arrow, where Aristotle was thinking that an arrow would propagate in space because it's sustained by its own velocity. In modern times, we would say that the velocity is sustained by the recirculation of the solvent. But anyway, the message is that you really need to take into account at 2 degrees of freedom systems, a particle and a solvent, in order to have a proper description. Can we do that by a coarse graining? Well, yes and no, depending on the problem under study. But it's important to remind that if you need to coarse grain a system, you would not consider the time evolution of these coupled fields. Next, if you do a simple, so to say, hydrodynamic treatment of the system, you need to remind that these things happen basically at the macro scale down to the molecular scale. In fact, hydrodynamics is a rather pervasive type of thing. You would see the same pattern if you look at the immediate neighborhood of a particle, of a molecule. Then some theoretical treatment could be done, but many body motion would be increasingly hard to treat. And finally, if you have a systematic flow, like a current, an overall current pushing the fluid here, it would be hard to treat in theoretical terms. So one answer can be treating the system in computational terms. And here, our approach is what is called the concurrent multiscale approach. We will focus basically on particles floating in a viscous fluid, and we need to treat computationally these 2 degrees of freedom on the same footing. What do we mean with particles? Particles here are objects which are suspended in the fluid, and they are designed to carry essential information about, for example, a molecule, and they are basically driven by forces. So the basic ingredient which would create a motion of particles would be forces. Therefore, you need to update the velocity, the state variables of this object through Newtonian mechanics, stochastic mechanics, if noise is there, or some other types of equations. At the field level, at the fluid level, you would have some sort of continuum dynamics. You may choose different types of dynamics, like Boltzmann equations, Navier-Stokes equations, or some other fancy type of evolution. And the important ingredient here is no more forces, but the transfer of momentum between different elements of the fluid. Finally, in order to have a working multiscale approach, we need to design to have a proper coupling between these 2 levels. So this coupling could be some sort of exchange of forces or momentum, or what we call in proper terms a feedback. Let me speak about the computational tools we've been developing. Some of them are well-consolidated computational tools like molecular dynamics or a solution of the Navier-Stokes equation, but coupled together in a novel way. we update the position of suspended bodies in the fluid through molecular or stochastic dynamics, which are solved by finite difference scheme. And the fluid would be solved at the Navier-Stokes level by some special way of solving it, which is called the Lattice Boltzmann method. Moreover, if noise, thermal noise, is present in the system, because we are treating, for example, something at a mesoscopic level where noise cannot be neglected, then we need to take into account of what is called fluctuating hydrodynamics, which is basically the Landau description of hydrodynamics. So what are the basic elements of this coupled scheme? Well, at first, we need the Lattice Boltzmann method updates the position of particles between grid points. So we have a grid point here in this small cube, which is displaced to neighboring points, in this case 18, via some type of mechanism. This mechanism basically is driven by what is called an update equation for the single particle distribution function f, which is the probability of having a particle at position x, time t, and a velocity v. Once we discretize this object over our mesh, we'd have an update scheme which looks like that. The distribution function f at time x plus some displacement, at time t plus some displacement, is equal at the same one at the previous step. This is called a free streaming term, plus some local relaxation term, which will drive the distribution function to relax towards a local Maxwellian. If you take these three terms of this equation, you can demonstrate that basically you are solving to some accuracy the Navier-Stokes equations, so the typical evolution of fluid of a moving fluid. Next, in order to have suspended bodies in our system or a fluctuating type of environment, we need to add two more bits. One is a term which is basically giving the momentum exchange with some surrounding body. And finally, inject some fluctuations in the system in the form of fluctuating hydrodynamics. So I'm not giving you the explicit form of these terms, but they have been described in the literature. Anyway, the particles move according to, in this case, to some modified Langevin equation. So the acceleration of the particle is given by mechanical forces, plus some friction, modified friction, which would feel the imbalance of the velocity of the particle locally in space and time with respect to the fluid velocity. And finally, there will be a noise happening at the particle level. Here, these two terms are basically, they are basically reciprocal of each other because you need to balance momentum between the 2 degrees of freedom. And finally, the noise happening here at these degrees of freedom and at these degrees of freedom need to enforce a typical theorem in statistical mechanics, which is called fluctuation dissipation theorem. Basically, thermal fluctuations must be the same at the two levels. Some words about why we chose this scheme. Well, there are a number of reasons. The first one is that Lattice Boltzmann is basically a way to solve the Navier-Stokes equation, which is rather accurate, in fact. It's second order accurate in space and time, and basically solves the fluid motion in the regime of what is called low Mach number, which means we are well below the supersonic regime, well below the speed of sound of the fluid. Also, we are solving the problem in what is called the not too far from equilibrium condition, which is governed by some number, which is called the Knudsen number. So basically, we are solving the evolution of the distribution function at low Mach and low Knudsen, which is enough for our purposes. Then we have some advantages with respect to solving the Navier-Stokes equation by brute force. Basically, we are disentangling a nonlinear term in the Navier-Stokes equation, some quadratic term in velocity. So this is a disentanglement of spatial and velocity discretization. These are quite technical. Also quite technical is the fact that we can handle boundary conditions in a very simple way. Boundary conditions may be a wall, some restriction of space in the system. And more importantly, we can modify rather easily and successfully the equations, the simple equations I showed before, in order to host more physical levels of the fluid. For example, we may want to have a complex rheology, non-Newtonian rheology in the fluid, and this can be done in very simple terms into the equations of motion. We can host an embedded particle into it, suspended bodies, by exchanging forces and momentum easily. And finally, the method is a local method, is a grid method, and is rather prone to parallel implementation. Sure.
About the answer. If you go back to the previous slide, so you have all these coefficients there.
Right.
That have to do with friction and things like that,
right.
that are actually physically determined on the next smaller scale than what you're talking about. And so is that like a parameter, or is that part of the multiscale approach that on a different scale, a different physics is used to calculate?
Okay, here we have basically two parameters which are important. This omega here, which is the viscosity of the fluid. So the viscosity is the macroscopic transport coefficient of the fluid. And next is this gamma. This gamma is basically, is not a friction in proper terms. It's more a coupling parameter, which is in the inverse of a time, between these 2 degrees of freedom. So it's the response of the system to the time the system responds to the perturbation in the fluid motion, in the particle motion. So this is a free parameter that we can choose according to some physical intuition.
But it's not a parameter that's modeled on a different scale in this equation.
In a way, it's a parameter which is a macroscopic object, if you want, because it's a friction, but we chose it according to a physical description of the system. And for next application, I will tell you more about that. Also, it is important to say that this viscosity we plug into the system is a bulk viscosity of the pure fluid. But of course, once you embed particles in the system, you modify the viscosity. So you have some complex rheology happening by itself. So it's emerging spontaneously.
Could you get the value of that parameter by some kind of simulation at a
Omega?
scale? No, gamma.
Gamma.
Yes.
You can, for example, you can use Stokes' law to predict a value of gamma. So you can have a pretty good prediction of this value and use it in your system. But again, it's a macroscopic prediction.
That's what I was asking, is whether you can use a microscopic simulation.
I think you could, but
Like, let's say from molecular dynamics.
exactly, you could use that. But that would be the same as having a viscosity which is predicted at the microscopic level via some Green-Kubo prediction. Then you could predict these values from bottom up and then plug them in your computational scheme. So you could do that in principle. Either predict them or use them.
Here,
I didn't do that here. Yeah, I didn't do that here. Okay, I'm going backward, sorry. Now, I was talking about parallel implementation. Why? Well, because it was rather important for us to think in big terms, meaning that we had in mind large systems, large simulations, and basically we needed to develop some tool, some code, some software, which would run on the Blue Gene machine. So massive simulations with Blue Gene. We have written this code, which is called MuPhi, stands for High Performance Multiphysics Multiscale Software, which has a number of technical things. I'm not going to describe them here, but just to give you some hints. At first, it uses a domain decomposition, which can be a standard Cartesian decomposition because you are partitioning the system you are simulating in basically in cubes or slabs or whatever. Or you can do something more sophisticated, as we did for hemodynamics, where you have basically a system which is not filling space in a homogeneous way. So you do some graph-based partitioning. And moreover, if you have a system which is very sparse in computational terms, as for example, many particles accumulate in some region of the computational space, which would be floating around, you need to basically spread the computational load over different processors, so it's not more associative between the domain decomposition and the processor. So this adaptive computation would allow us to circumvent the sparsity bottleneck. So here are some results we've been taking by running on the Harvard Blue Gene for a rather small system, if you want. It's made of 100 basically cube mesh points and about 4,000 particles. We have basically a linear scaling of our performances. And basically, the Lattice Boltzmann is really a piece of cake because it's basically close to the ideal value of perfect scalability, while the joint Lattice Boltzmann molecular dynamics, it's a bit below, but still with an efficiency of 50%. This data basically means that we can run for up to 2,000 processors by cutting down, speeding up 1,000-fold our simulation, which means that we have gained 1,000 times in speed. But also, we've been running on some much larger machine, like a Blue Gene at IBM Research Watson with 32,000 processors, and we observed basically the same features. Linear scaling up to 32,000 processors, and Lattice Boltzmann even super linear because of cache reasons and some other technical reasons. Basically, this means that we could run 16,000 times faster than on a single processor with a system made of 500 cube mesh points and about 256,000 particles. I think this was pretty neat because a speed up of 60,000 is something which is really nice in computational terms. It's quite a cut down. And taking these together, we could say that our code is rather prone to petaflop computing. It can scale linearly up to 32,000 nodes and most probably beyond because it doesn't show signs of saturating. And it is important to mention that these data couldn't be achieved on a different architecture. These are really peculiar to the fact that the scalability of communications on Blue Genes are really unique. Now, once the table has been set up, let's go into the description of results. The first one is about biopolymer translocation in nanopores. What is this about? Well, a biopolymer, as DNA in this case, is usually translocating through different channels in biological systems. This is typical when you have a viral infection, where basically portions of DNA get through some channel into the host cell. Or, for example, when you have the passage of proteins into channels to go through in and out of cells. But in our case, our interest was for a different reason. We were interested in studying what is called ultrafast sequencing, which is the possibility of basically forcing DNA to translocate across a solid-state nanopore, like in this case, and reading off really quickly the information in each base pair and reconstructing at a later stage, or maybe in real time, the information related to each base pair. So the goal of many experimental groups nowadays is to do ultrafast sequencing by reading off this information really quick and really cheap as compared to current methods.
Excuse me, what exactly are you measuring as he goes through the channel? What are you measuring the velocity?
In experimental terms, what people measure is the current of counter ions going through a hole, so through a narrow pore, which is a function of the presence of the DNA inside the pore. So basically, you are measuring what is called the current blockade, which is the fact that you are occluding part of the available space for flow of counter ions inside the hole.
And is there any effect of one molecule going through on another molecule going?
I will talk about that, yes. But of course, this signal will be modulated by the presence of a specific base pair inside the pore. In our case, we've done different studies. The first one is about single file motion, which is the fact that a polymer, a biopolymer, or a polymer, generically speaking, is translocating between two chambers in this computational setup. The two chambers have a hole, and the hole in this case is small enough so that you basically have one monomer per unit time passing through the hole. So this is what we mean with single file motion. We will deal with fast translocation regime, which means that we are pulling this polymer here by applying a localized force at the pore level, and this force is large enough so that the translocation time is much shorter than the typical relaxation time of the polymer, which is called the Zim time. So basically, we are pulling this polymer rather quickly so that the polymer has not much time to relax back to its equilibrium configuration. So this is really an off-equilibrium experiment. And finally, we will not include chemical details about DNA here. We will consider what is called double-strand DNA, which is a chain of base pairs which has some specificity. In particular, has a persistent length of about 150 base pairs. The persistent length is the length over which the DNA chain basically loses its own rigidity. So our computational molecule atoms of the chain, the red spots here, basically represent 150 base pairs, which is about one persistent length of double-strand DNA. We could add some chemical specificity, so simulate something more like a double helix, if you want, but we didn't do this now because we were more interested in the statistical behavior of this polymer through translocation. This is a clip of a rather short polymer translocating through a hole, and what you see here is two things. Blue spots, which are the monomers of the polymer translocating, and the red thing, which is the hydrodynamic fluid, the intensity of the hydrodynamic velocity locally, which is following basically the motion of the polymer through translocation. You see that this is a rather rapid event. It goes rather rapidly. You see some noise happening here because of the system. It's at the mesoscopic level, so there is some fluctuating hydrodynamics happening. But also, you cannot appreciate from this picture the coherence of the bead motion together with the hydrodynamic motion because it goes too fast. Here there are about 100 time steps per frame. But you can follow this in more detail if you look at the same clip shot at much shorter pace, which is 1 frame per time step. You would notice that the fluid flow follows like a shadow the motion of the polymer, and there is a high degree of coherence of the molecule through translocation and the hydrodynamic field. This coherence means different things, but anyway, you can think of as a ball of hydrodynamic field which is trying to squeeze through the hole while the translocation passes through. So there are different ways of describing this system. However, it is important to check to see if the system is showing some hydrodynamic signature, which means if the hydrodynamic field is really affecting the motion of the polymer. Here, experiments have measured what is called the translocation time tau versus the length of the polymer. And this is a typical scaling law, which is shown to obey a power law with a power exponent of 1.27. And some explanation have appeared in literature in order to explain this data. But in our case, we started by simulating the system in presence of a solvent, of hydrodynamic solvent, or in absence of some sense of it, which means basically simulating with a Brownian type of environment. With the fluid, so with the hydrodynamic fluid, we got an exponent of 1.28, which is very similar to the experimental one. And without a coherent fluid, which means only a Brownian type of solvent, we got 1.36. So you can tell from this data that the signature of hydrodynamic presence is rather clear. But the other question is how to explain data. This is another clip showing the translocation of a number of chains here. Here the representation is like a cloud of different chains translocating from up to down. And basically each monomer is represented in some sort of cloudish way. But this representation allows you to appreciate the fact that the polymer, prior to translocation, is in an open type of configuration, what is called, in technical terms, a mushroom type of configuration. And once translocating, it has no time to relax back to the initial configuration. It stays in some collapsed type of state, which is rather homogeneous and isotropic. By looking at this clip, we realized that basically we needed to describe this data in terms of scaling relations, which are basically given by Fleury type of description in polymer physics, by looking at the longitudinal and transverse components of the gyration tensor. Yes?
If you go to the previous simulation, the fluid is this noise we see?
Yes.
And what is the red thing?
The red, no, sorry, the blue are the beads of the particle.
On the fluid.
This one or this one?
On the noise. On
The noise is typical fluctuations in the velocity field due to the fluctuating hydrodynamics. So it's noise.
And the N on your exponent in the next slide is the number of what?
Here is the time the polymer takes to translocate it.
No, on the equation there, N, the big
Yeah.
N is
Okay, this is the length of the polymer.
the length.
Of the polymer, yes. So you want to see how fast the polymer translocates with the length of the polymer. Here you can appreciate that there is lubrication happening because basically the time to translocate goes shorter for in presence of hydrodynamics. So it's really a lubricant in mechanical terms. Anyway, if we do some scaling analysis for the different components of the gyration tensor here, we can basically reconstruct a phenomenological theory which is basically based on the rate of work injected into the system by the external field and by the hydrodynamic field. By doing this balance equation, we can interpret data and reconstruct basically this equation starting from macroscopic arguments and the output of simulations. So a further step in the translocation of DNA of a biopolymer in a nanopore is what is called the multifile translocation. This is a slightly different setup of before. We have now two chambers. Nothing changes here except for the size of the hole. Basically, we are allowing now that some correlations happen between the two chambers, both at the configurational level of the polymer and at the hydrodynamic level of the solvent. And by allowing this, a number of effects take place now. In particular, we were driven by some experimental data, experiments done here at Harvard, where people were measuring the current across the two sides of the nanopore as a function, for example, of the size of the pore. And they were observing that for short enough pores, not as short as the single file, but slightly larger, the signal of the flow of counterions across the two sides is basically showing some sort of spot-like behavior, which means basically that sometimes the flow is a constant and it's basically given by this type of signal, so it fills some available space to translocate. Sometimes you feel a different type of signal that was interpreted in terms of double file or triple file type of configuration inside the nanopore. So we were interested in reproducing this data and understand the local structure and see how hydrodynamics could affect this data. Just to give you a snapshot of results, we've been doing pretty much the same type of simulation of experiments in computational terms, where basically we were simulating different translocations of a number of polymers with different size of the hole and measuring basically the same type of thing, which is the available space for counterions to flow back from left to right in our computational setup. And measuring, for example, the residence of monomers versus time during translocation for 3 different hole sizes. Different colors here mean the fastest translocation event, which is supposed to have many monomers clogging the hole, or the slowest one, which is the red one, and the most probable one, which is the green one. And measuring, by inverting basically this data, the current in some histogram, which is should be basically what experimentalists see. And we could basically reproduce pretty much the same data and see some banding, which is a signature of what is called quantized current blockades. In fact, since the system can go in double, triple, or even higher number of configurations inside the hole, you would basically see multiples of some typical current. And as soon as the hole size gets larger, these currents are distributed over a continuum. So these were the data that were interpreted in different ways. And basically, we could see that the hydrodynamic effect is still important, which basically renormalizes this data by some basically constant value. And I think this was pretty neat, because we could really reproduce some sophisticated effect taking place, which is an interplay between short distances at the pore level and the configuration of the polymer. Yet another exotic example of polymer translocation. This is called Multihull Translocation. Again, this is a setup which has been realized in laboratories at BU. The scenario here is much more complicated than before, because there are a number of polymers competing to go through different holes. Here, this clip shows you a number of things, but basically there are 4 polymers. Each one has one hole assigned, in principle, in order to go through. Each one has a pulling force localized at the hole level. But we've seen that these events have really a rich type of scenario. For example, there are a lot of snapback and retractions of the polymer, which means that the polymer tries to go in, and at some point it gets a retraction for some entanglement reasons. There can be, therefore, entanglement, a release of configurations. And finally, there could be some effect of the hydrodynamic coherence. This is still a work in progress. Just to show you the richness of this phenomenon, you see basically 4 polymers. The green and the blue are competing to go through different holes, but finally you see that the green one basically swallows the light blue one. And finally, the translocation happens by 2 polymers across the same hole, while the other 2 polymers basically translocate in a normal way. So all these data need more extensive simulations. We will run up to 64 holes for about 250,000 atoms on the blue gene, and this data will need some further inquiry and interpretation.
And does the distance between the holes have predictable effect?
It should do, yes, because the shorter is the distance, the more the polymers get entangled with each other. So they have a difficulty. We still don't have data on that. But this is really a sensitive parameter for our simulation. That's right.
Why do the polymers not knock up and not go through at all?
Well, every now and then they would not, and basically wouldn't like to go through. But it is important to realize that this system has noise. And noise is a powerful lubricant, if you want, because it allows, sooner or later, to go through. There is also a subtle concept here, which is connected to the self-retraction event. Sometimes you pull the polymer to go through. It will respond to your pulling force. But every now and then, it will snap back, because it will accumulate a lot of elastic energy. So one single event may really violate the second principle. So it's really something amazing to look at this. I don't have the clip here, but I can show you clips privately if you want. But the fact is that if you take an ensemble of events altogether, the statistics would not violate the second principle. Individually, they can. The pulling force, how strong is the pulling force? How does it work in reality, in experiments? Well, basically, they can really focus. It's an electric field, and they can really focus basically by building up some special device the electric intensity at the pore level. So it's really a localized type of field. So the next chapter about multiscale computing is about hemodynamics. Hemodynamics is a large field. In this case, we are interested in the genesis and evolution of what are called plaques, and I will describe them in a moment. This is a picture of the heart, and basically, arteries are a branched type of environment of vessels which carry oxygenated water, blood, away from the heart. Each of us has a rather peculiar topography of the arteries, and doctors want to study this hemodynamics in detail for a number of reasons. Well, at first, they can really reconstruct to high accuracy the topography of these vessels here and provide accurate measurements of the lumen of the arteries locally in space. Why do they study this? Well, because basically arteriosclerosis is the typical social disease that they want to study and eventually prevent, which is basically the accumulation. This is a section of an artery, which is the accumulation basically of fat and lipids at the inner part of the wall, which takes place across different years. Basically, it starts when we are teenagers. And it starts for a number of reasons, basically because we have some bad cholesterol accumulation inside the wall of these arteries. The immune system responds to this accumulation by sending some macrophages, some white blood cells here. These white cells are unable to absorb this cholesterol, and they get disrupted, and they get absorbed basically by the wall of the arteries. And since they carry some cholesterol themselves, basically they accumulate more cholesterol, and then the immune system responds by sending more white cells, and it's a cycle. And in the end, this accumulation of lipids here grow into some bumpy type of shape. So it's really an occlusion here. And in many cases, it becomes a very strong occlusion, like here. And basically, when you get up to 50% of obstruction of the lumen, there is a high risk that this plaque here would break. There would be a sudden emission of lipids into the blood, and a heart attack would happen. So the point here is to study what are called the vulnerable plaques, those regions of an artery which could be really vulnerable to rupture. So we wish to understand this. And this is a large project, and we are still at the beginning. But just to give you some hints of what is the physical mechanism of plaque formation, genesis, and rupture, basically it's, again, an hydrodynamic problem. Imagine now that the plaque is some sort of obstruction here, and basically the streamlines can have two different shapes, depending on the velocity of the fluid. If the velocity is slow, for example, well below the Reynolds number is the characteristic number of hydrodynamics, which is below 0.1, the streamlines look laminar and undisturbed, just like in the first slide when I showed the moving ball. Now, if the velocity goes higher and the Reynolds goes up to 50, the flow becomes disturbed, still laminar, but disturbed, and basically you would observe some recirculation points. So the disturbance of this field has profound implications in the formation of plaques. In fact, you can tell that in a real vessel, something like that and something like that happens. I thought this was a picture, a drawing, but instead this is a real, and this is being created by a real vessel. It's a photography of different streamlines done by some doctors. And you can tell that basically you get an undisturbed or disturbed laminar flow in different regions of the arteries. And there, you would see some recirculation points in different regions, like past some bending here or close to some bifurcation point, which is basically similar to what happens to a river past a rocky spot. What is the physical quantity which drives a disturbed versus an undisturbed laminar fluid? It's what is called the endothelial shear stress. So it's the shear stress of the fluid close to the wall of the vessel. You have basically two types of flow. This is a typical laminar flow. And it is important to realize that the internal wall of the artery responds differently with the value of the fluid velocity, sorry. So if the fluid velocity is rather high and laminar, you will get some sort of smooth surface. So it's some really ordering of the underlying fluid vessel wall. While if the flow gets disturbed, like in this pulsatile type of flow, the surface gets rough. If it gets rough, you get a lot of exchange of chemicals and a lot of biological activity going on between the outer and the inner part of the wall. So this is vasculoprotective, this is not. What I'm saying here is that we are not going to model this complicated scenario here, which needs a lot of computational details. But we have ideas on how to model this in order to have basically a fluid flow in arteries, which takes care of having an underlying fluid flow and basically the evolution of plaques. Before doing that, I hope I can convince you that we can simulate real arteries. These are real arteries taken from patients. This is a branched artery of about 3 millimeters. You are looking here at the shear stress versus time from two different views, front and rear. And you can tell that basically the pattern of shear stress here is rather peculiar. So you would get some low shear stress, the blue one, or high shear stress, where the more reddish one is, depending on the position of the vessel. You can see this shear stress distribution in different locations and see that it is rather patterned. You can take cuts of these vessels in different positions, study, for example, the current of the flow or the shear stress, which look in one case as a parabola type of flow or an inverted parabola. And you can also study more complicated situations, like in the case of bifurcations. Bifurcation, again, is a case where you have a lot of flow going on, but basically regions of low shear stress close to the bifurcation point. So these are different cases, either realistic or more idealized, where you can really study the vulnerable spots and the formation of plaques by adding to the system some ingredient which tells us how the plaques evolve. We can even do pulsatile flow, which is easy in our setup. This is, again, the realistic vessel. You see basically bands of low shear stress propagating across the vessel. Or for the case of the bifurcation, some sort of complicated pattern happening here. And you would see really a band of low shear stress propagating, which can be dangerous in principle. And if you look inside this vessel, from inside, really navigating through the vessel, you would see really this band propagating through the vessel in some peculiar way. So these are all typical cases which need proper investigation. There's a complex time dependency, which depends basically on the typical pulsatile pattern. And there are space-time and time-local vulnerable spots. So I think it's time to end this talk. Just to give you some conclusions and prospects, I hope I convinced you that multiscale computing is nowadays a mature technique, especially for the problems we have in mind, since we have a consistent and physically meaningful way of connecting different levels of description. We can do ultra-fast computing via Blue Gene or some other type of architectures. And we can do something which is called real-time solver for hemodynamics. Basically, we can simulate a vessel with a computational time which ticks at the same velocity as physical time, which is not too bad. I didn't tell you that, for example, the vessel from before was simulated for 5 minutes computational time on this laptop. If I ran it on a Blue Gene, it would take really the blink of an eye. And finally, the visual aid here is really important because we have a number of problems where we need to visualize particles and fields moving. We need to look at streamlines, so velocity patterns, tensorial patterns like stress evolution, critical regions where we need to recognize delicate spots, vulnerable spots, noise reduction, because often we have a noisy system, and many other reasons. So these are basically the 3 milestones that we need to address presently and in the future. Thank you very much for your attention.